Hey, and yet again, we're super excited to have you all for the course in December, 9th and 10th of December. This is the second week of the preparation material, and last week we talked about different reservoir fluids. We also gave some recommended reading material about some vocabulary and also what is different from different reservoir fluids. And we're going to take that a step forward now and talk about something that's very, very important to understand when it comes to PVT in the entire petroleum industry, actually, because the most common thing or the most common way that we represent PVT properties in the petroleum domain is with the so-called black oil PVT model. We're going to talk a little bit more about that black hole PVT model right here. And we're going to also look at a few of the key assumptions that goes into the black hole PVT model and do an exercise related to that. So before we jump into the weeds on the table themselves, it's just a quick reminder to everybody that all PVT properties that we talk about, they're a function of pressure, temperature, and composition. That's the essence of PVT in general. And if we think about this a little bit, we can see that this is actually a very complex space with 2 plus n dimensions, where n is the number of components that we've defined in our system. Okay, but a way to simplify this complexity is to assume that the number of components that make up our petroleum system is 2. So being a surface gas and a surface oil. And that's what really makes up the basis and forms the basis of the so-called black oil model. A very important note regarding the black oil model is that black oil models and the way we represent it through black oil PVT tables can be used for all reservoir fluid systems and not only for black oil systems. So then the question is then, why do we actually call it a black oil table? And it's a good question. And the little bit disappointing answer is that it's just tradition. And it has to do with that this is a 2-component PVT model where the one component is oil in the tank, and the oil in the tank, at least back in the days, was always black. And then the other component is surface gas. A more appropriate name for this model would probably be the 2-component PVT model, which was suggested by Keith Coates, one of the pioneers in reservoir simulation, which we all think it's a good suggestion. So just remember that you can use black oil tables for all kinds of different reservoir fluids. Okay. In a very simplistic graphical manner, we can say that a black oil table consists of, it's a table, obviously, of 7 different columns, and it's generated for a constant temperature, where one column is pressure, and then we have 3 properties for each pressure associated to each of the different components. And here we have 2 components, so oil and gas. And we'll talk a little bit more about these different ones in the next slide. But the key essence here is that black oil PVT tables are used for essentially all different petroleum engineering calculations. You use it in reserves, you use it for process, you use it for simulation, you use it for RTA and PTA, kind of well testing analysis, pipe flows, etc. So it's really, really at the core. And the way, or what is actually needed to create one is what we'll talk a lot about in the course, but in short, you need an equation of state model that you all have now. You also have it in the software that has been handed out. You need to input a temperature for reservoir simulation. That would be the reservoir temperature. You need a composition, and we've seen that last week, how we can generate these compositions from readily available data. And then, of course, a surface process that's representative for that particular field. So just to recap on the black oil PVT model, we just talked about that it's essentially made up by 2 components, oil and gas, and then there's 3 properties defined for each component. We also talked about that, where the composition, so the amount of surface oil to surface gas, is represented for a oil phase, which is why we use green as the solution, GOR, and for the gas phase it will be the solution CGR, also called R, capital RV in many simulators. The way we link surface to reservoir volumes, for instance, would be through the formation volume factors, and then we also have viscosities for each phase. Important to note is that the surface oil and gas densities are assumed to be constant, which means that if you are talking about a two-phase system, for instance, you have condensate in solution with the reservoir gas and you have surface oil in solution with the reservoir oil, if you like, both of those surface oils are assumed to have the same density, and the same goes for gas. The other thing is that all the PVT properties in a black oil table are generated assuming a constant process. Okay, so we know that PVT properties are process dependent, but they're assumed to be constant when you generate the table. And again, the reservoir temperature is also assumed to be constant for one black oil table. So if you look at all these different properties and relate them to reservoir volumes, so if the reservoir volume is just a large V subscript G, and we have the oil volume being a V subscript O, we can define these different volumetric properties, so the so-called BGD, little rs, BO, and capital RS. And we'll talk much more about this in the course. But what's important to emphasize when it comes to these four properties is that they are process dependent, and process dependent is what it means in layman terms is that if we change the separator conditions, if we change the surface process, if we add a separator stage, if we remove a separator stage, these things will actually change even though the composition going into the process is the same. And we'll exemplify that with an exercise after this video. While the viscosities, they're surface independent. So to put this in perspective, we typically talk about these process dependencies, which in very condensed way would be that phase split volumes depends on pressure and temperature conditions and the path to get there. And GORs and formation volume factors are process dependent, meaning that if you were producing a barrel of oil from this field through a very complex process, and this would be your sales oil and sales gas, that would be different than if you took this straight to stock tank conditions. And it would be different if you actually measured that GOR at a set of test separator conditions, which is not stock tank conditions. Okay, so it's the same. We're producing the same composition, the same fluid, but the resulting products are different, and hence the GORs and information volume factors would be different. And in this case, that will have an impact on the GOR being going from 8,400 to 9,250 for the single stage flash, which is more inefficient. And at separated conditions, you will get typically a lower GOR, in this case 6,700, for example. So that's very important to know the path to get there. Know the fact that when we're talking about PVT properties, we're actually, even though we're talking about volumes, which is kind of unique for the petroleum industry, and you see that here, when we talk about volumes, we talk about a stock tank barrel, we're talking about a separator barrel, and we are talking about a reservoir barrel, and it's kind of unique to have a nomenclature where you define a volume, but you also have to put that volume into a context, be it reservoir conditions, separator conditions, or stock tank. Okay. So on that, I wish you good luck with the exercise, and just let me know if you have any questions.